Okay, in this video we're going to talk about comparisons once again, but this time we're going to deal with a question that's asking about the power generated in an object. So if you recall, the power is the work over the time. In other words, it's how fast you do work. So the units of that is watts. So the problem reads, a rocket requires 600 watts of power to reach an altitude of 100 meters at some speed v and at some time t. How much power is required to reach the same altitude at a speed of 2v and a time of t over 2? So again, this is going to be a basic comparison, but where do we start with these? I mean, how would we even know where to begin with this? Well, the first thing that I would do is I would start by defining the definition of power. Okay, so if we talk about power here, there's a couple ways to think about it. You can think of it as the work over the time, how fast you're doing the work, or we can think of it as the force times the average velocity. We're talking about average power, let's just say. Now if we look at work down here, this work over time is actually related to this. I'm going to show you where that comes from. But the work we know is going to be what? The work is going to be the force times the displacement times cosine of theta over the time, some delta t. I'll just put delta t here. Okay. All right. So the rocket's going up, and I'm going to assume that the net work obviously is going to be in the direction here of the rocket's motion, like this. Okay. And the rocket's going to move up some delta y, like this. Okay. So my work is going to be in that direction of the delta y, like this. And it's going to go up to some height there of, we said it's going to go 100 meters. Fine. So my cosine of theta, my angle of my displacement with my net force, they're lined up together, right? So I know that. So my net force is here. So the angle between those two vectors is just 0. So this term just becomes 1. So the power is just going to be the force times delta y over the time, over delta t. And what is force? What is force? Well, force is mass times acceleration, okay? Delta y over delta t. Now, I'm dealing with this equation now in terms of mass, acceleration, and displacement. And again, this is the same equation. I'm just bringing it down here and condensing it a little bit. But my equation told me that I'm started with a speed of v and I'm going to go to 2v. And I started with a time of t and I'm going to go to t over 2, or 1/2 the time. So I want to go twice as fast in half the time. But right here in this equation there's no velocity, right? So how do I deal with that? How do I get velocity in here and time? I have acceleration but not the velocity. So well, I have to start thinking about this in terms of acceleration. What is acceleration in terms of kinematics? If I have a constant force, I can kind of remember back here for a second. I'm just going to kind of do like a little think back here over time. We can define acceleration from this equation. The final velocity squared equals the initial velocity squared plus 2a delta y. And if that rocket starts from rest, right, and it moves up, that initial velocity is going to be just 0. So if I want to define my acceleration in these terms, I can start dividing everything over, right? I can say v squared over 2 delta y equals acceleration, right? I just divided these over, right? So what I'm going to do is I'm going to take this definition of acceleration for a constant acceleration, and I'm going to plug it into this equation here. So I'm going to get rid of the acceleration here. So now instead of ma delta y over delta t, I'm going to have m times, and I'm going to write this in a different color so you can see it. This one is going to be in blue over here, just so you can see it. Wherever the acceleration was, I'm going to put in here v squared over 2 delta y here. Okay, so I just substituted that particular portion in here, right? Times delta y over delta t. In other words, everything is just the same except for my acceleration. Now I can start to think about what I want to do, because I have velocity here, or speed, however you want to talk about it, and I have time. So I can start to deal with some issues here. I can actually start to express this equation how I want to. So this is really kind of the hardest part of this problem. is figuring out how you want to express that. Well, first of all, I can start to cancel out some terms. The displacements are going to cancel out like that. Okay, so I'm just going to end up with a governing equation here in terms of mass, velocity, and time. And that governing equation is going to be mv squared over 2t. I'm just going to write it as t instead of delta t because we're starting from 0. Aha, so now I have something I can deal with. Okay, so I'm going to do my comparison now. Okay, so I'm starting with what? 600 watts. This is my initial power. Okay, so just so we can go down here and I can just say, okay, my power initial is 600 watts. And I'm going to do a comparison here now. Okay, so when I do my comparisons, remember I take my governing equation and I plug in 1 for everything to start out. So my power here is going to be 1 times 1 squared over 1 times 1. Okay, again, I'm just plugging in 1 for everything as a basis. This only works when you have direct and indirect variation, but it works great in this equation because that's all we have is a jumble of products and quotients. So I'm starting out with 1. That's my power initial. Okay, so what did I change here? Well, here's what we changed. We basically took, I'll rewrite this here. We basically went from v to 2v. We went from t to t over 2. Okay, so that's basically what I'm going to change here. So I started with this. Power is 1. Okay, power initial is a factor of 1. And I'm changing now the v to 2v. So the mass doesn't change. I just put in 1 because that's the mass, right? Didn't do anything with the mass. But the speed definitely changed. Instead of being 1, I'm doubling it. So I'm just going to put 2 here because we're dealing with ratios. Over 2, that doesn't change. That constant doesn't change. And the time is just going to be 1/2 of what this one was here. Okay. So now when I go ahead and deal with that, I have 4 divided by 1/2, which is just going to be 8. So this is a factor of 8. In other words, it's 8 times the original. So the power final is 8 times the original. So, very simply, I can now say that my final power, if I write it here in red, my final power, okay, in terms of my new speed and my new time, is just going to be 8 times the original, right? So it's just going to be 8 times 600 watts. So I'm just going to end up with 4,800 watts to move that rocket over the same exact displacement when we're dealing with twice the speed over half the time. Okay, just to summarize, we had a problem that showed us some amount of power in watts to have a rocket reach some altitude at some speed v at some time t, and they want to know, well, how much power is required to reach the same altitude at a speed of 2v in a time of t over 2. So again, the hardest part of this was finding the governing equation. I started with work over time, worked it down from force times displacement cosine theta over t. We got force displacement over t. I ended up with mass times acceleration delta y over t. I had to express acceleration in terms of speed and displacement. I went ahead and did that. They canceled. My governing equation is now a function of mass, velocity, and time. Then I went down to my comparison. The initial one always starts with 1 is everything, so my initial basis is 1, and then it's very simple there. I doubled the speed or the velocity, so I put 2 there, and I did half for the time. I put half there, and I ended up with 8. So I know that it has to be 8 times the original power. So the final power is just going to be 8 times 600 or 4,800 watts. Alright, that's all I got for this video. Thanks for watching, and I'll talk to you soon.